All right. Thank you for coming today. Today we'll be talking about some new set of storage patterns that are because the environment that we're deploying our storage system is changing. Oops. Whoa, a little sensitive there. I'm here with Kyle Schockenmeyer, and my name is Luis Pavon, and we both work for Portworx. So one of the things that you've probably seen these slides before. I have the same slides from, I did a presentation last year at Linux Vault, where I tried to describe the journey of storage system being containerized. And one of the things that's happened is that this is our traditional storage model. We have a compute on one side and storage on the other. And we have some type of interconnect for I/O in between. And we've used this model for pretty much forever, since the beginning of storage. So we've had open systems, we've had virtual machines, but what is new? And this is quite sensitive. Yeah, this thing is like going two things at a time. But containers is the new thing, okay? Containers is changing the environment that we're deploying our storage systems. It's changing the applications that are consuming the storage. And so when we think about containers, the way that they work is a container really is just an application that runs on your system that its resources have been constrained. That's really what a container is. So it's very simple to think about a container in a single node. But it is when you start moving to the enterprise, start moving to applications running where they have to be online all the time, you want what's called a container orchestration system, a CO. Now there's many types of container orchestration systems like Mesos and Docker, but we're gonna, it did it again. Look at that. I'm just gonna go to the mouse, forget this. Yeah, thank you. So I like walking around and now I'm stuck here. So what we're going to do is that we're going to concentrate on Kubernetes, right? So I'm not going to read this for you. This is just from the website. But think of Kubernetes as the operating system for the data center. When we write applications today, we always understand what operating system is going to be, we're going to run our application on. For example, when we write any type of application, we understand that we're going to be running on Windows or we're going to be running on Linux. Now we need to understand that the operating system, the system that's going to control the application, is now across nodes, okay, for an entire data center. So this now proposes a new type of storage architecture. And again, this is the same slide that I've been showing for multiple years now. But I want to really stress the new type of model. And that is that storage itself, when it's a software-defined storage, is just software. It's just an application. And with Kubernetes or any type of CO, you can now say, I want the operating system of the data center, the CO, to be responsible for deploying my application across the data center. So in this example, in this new storage architecture, what we have here is that we don't have a set of dedicated machines for storage and a dedicated machines for compute. The customer instead has spent some of their money to be able to buy n number of nodes. They didn't calculate it in that fashion. Some of those nodes have storage, and some of those nodes do not, okay? And some of the nodes that do not, for example, are maybe blades or something like that, and they're meant to run just containers. But the systems with disks, the user, the administrator of this entire system, wants to deploy a containerized application, so the container orchestration system can then deploy the application to those nodes, and then consume that storage and provide it back to the system. Okay? So, what does that mean? It means now that we have a new set of users for our storage system. In the older model, and this is like, now I'm really dating myself, way back when I worked at EMC, they would buy an EMC device, our customers. They had to wait until the the device was delivered to their site, connected, and during that time, some of their employees will be sent back to EMC to be trained exactly how to use the machine. Okay? We don't have that type of system anymore. These users do not want to go back to your company and be trained to understand how to operate your storage system. What they expect is immediate access. So, one of the things that happened is that their expectations have changed. Before, they went ahead and they got trained by the storage vendor. But instead, what they want now is, one, they want the storage system to be managed by the CEO. They don't want a separate control plane. They want the same one that they manage your applications for the databases and everything else, the same one, the same control plane for managing the storage system. They want to be able to install your storage system into the CO in the same way that they install other applications. They don't want anything different, okay? They also, what they want to do is that with this new model, okay, they want to be able to provide their users with new solutions. And then they want to be able to say, this is the biggest one, because some of them don't really understand how storage works. So they say, I want to deploy my application on this cluster or this, maybe on Amazon or Azure or even on-prem. And then I want to take my app and move it to another, to maybe on the cloud or from the cloud back to on-prem, right? But then when we say, well, yeah, but you forgot the storage part. Like, you can't just move the storage as easily. So then the comment is, well, I want the storage system to make this easy for me because that's what I want to do, right? The storage system to provide these primitives to be able to move the data across clusters from the cloud or back and forth so that I can satisfy my requirements. So one of the things I put the little faces there is because the first one is when these users start using traditional storage systems, it doesn't satisfy them. They get upset that it takes too long. Okay? The second one is that maybe we do something with the system that we integrated, but we don't do enough. So they're okay. They're not super happy, but they're satisfied. The third and fourth is when we say, oh, no, we have taken the extra work in our storage system to integrate the storage system into your CO. Okay? And this, what we're trying to describe here in our talk, is a major disruption to the way that we deal with the control plane in storage systems. Okay? What we do today is we're trying to say is that the storage system has to be not just something that just do two commands, reads and writes, right? It has to be smarter than that. It has to be integrated with the CO. It has to understand what the requirements are above just a simple disk, but going across the world, across clouds, moving data from one point to the other. It has to be able to support, for example, RBAC that is done from the CO's point of view. Okay? So what we're going to propose today is a set of storage patterns to be able to help with this new model. Okay? And I'm going to pass it to Kyle. Kyle, yeah, I think you have the mic.
Okay, cool. Can you hear me? Cool. So the first thing that we want to talk about is what the users expect. We kind of went over that already, but just to kind of clarify again, is they want a simple and easy to use experience. The users are the application developers. They're not the storage admins anymore. They're the application developers. Their applications consume the storage, and that's as much as they want to touch it. So traditionally, they'd have to go and speak to a storage administrator, get a volume provision, get access. It can be days to get a volume for any given application. It's also, you have to consider where the hardware is, who you're getting access to that hardware from. But now the new thing is that you can be able to consume this hardware as a user from anywhere. It can be on your on-prem data center through the CO, or it can be in the cloud. It can be transferring back and forth. And most of the users simply just want to get it working. They don't want to hear about, verifying that the performance is exactly as expected. They want to make sure that they can get a system that can scale with their needs, that can scale out, scale up, whichever way they need to go, can provide all the features that they want. So they just really want to go and try it out. So how do we do that? From a storage system, from a storage product perspective, you really have to design your system to work jointly with the CO. And that means everything needs to be approached from a top-down perspective. It's no more that you just have a bunch of storage servers with disks on them, and then you have to go find out how to access them. Now you integrate everything with the CO, and you're able to access them all through a single point. That CO is controlling your containers that are running your storage, is controlling your apps, and the better that they communicate, the better for the end user here. They get packaged together and through containers, and in so doing, you're able to cover a lot of the additional pieces like testing and being able to cover different platforms and different clouds and all of that. So if you make it really easy to containerize your storage and build everything together, then it actually leads you to be able to test it out and run it really quickly. So one example that we have is Katacoda is a website where you can run Kubernetes clusters, virtual machines. It's really good for like POCs because you can rapidly spin up an instance somewhere and then test it out, and it's free. So I'm just going to do a real quick demo, which shows that if you connect all the pieces of your container and your storage and your application, you can do something really quickly, really efficiently, and I guess I'm going to show that you can deploy and provision your storage on a Kubernetes cluster and get a volume in the snap of a finger. So let me move to my, cool. So if you guys can't see this, it looks good? Okay, cool. So Katacoda is, I've skipped the very first page, but it's basically a page that describes what we're going to do. But essentially, we've loaded up one of our examples, and it's launched a Kubernetes cluster. So I believe, there, we have all 4 of our nodes running. So it usually takes about a minute. I just went ahead and preloaded it. And then you can basically read through, I'm going to skip over a lot of this because a lot of it's setting up the PVs and the PVs, all of the persistent volume claims and that sort of thing. But essentially, with that cluster up and running, we can run a bunch of commands, and you can see that we've got our cluster here. I can't get the mouse to work, but it's a 3-node Portworx cluster. Oh yeah, actually, I mean these are actual VMs. They're all running. So this is a real demo here. Essentially, what you can do is copy paste pieces from left to right here, and it'll execute all the commands for you. So I'm going to skip over reading all of these pieces to everybody, but this is basically setting up storage classes with Kubernetes. Boom, it's done. And then we are going to set up a persistent claim volume. That's also on one of the YAMLs that are already preloaded. And then check to see if the claim was set up correctly. Cool. And now finally, create and provision and attach a volume. So in the span of about 30 seconds, we're able to get a volume provisioned and attached to an application. I don't have an application running, but it's now available to be consumed. So this is the kind of experience that the application developers are trying to use. They don't mind having to read all the YAML files. They can ignore that if it just works. But this is the experience that people are expecting in cloud native storage, is that they just want to be able to run it, fire off a few commands, see that it's up and running, and now consume the device. So how does a lot of this work? In the background, this is all Kubernetes. It's running, in this example, a Portworx containers on several nodes. And it's using a lot of concepts from the cloud, one of which is programmable infrastructure. And This is probably not new to anybody here, but the idea is that now if you're running things in the cloud, all of your different resources like your networking, your servers, the nodes themselves, your resources for I/O, disks, etc., they're provisioned and configured on demand. So you can add a 5th node to that cluster just by snapping your fingers, and the expectation is that it'll join the cluster and be happy. In these cases, everything's managed through an API. It's not managed really through a CLI. There's a CLI there, but the expectations from the users are that I should be able to consume an API through whatever tool or resource that I'm using and have this interact with my cloud providers. So examples here are having interfaces to AWS, GCP, UCS, OpenStack, etc. But what does this really mean for storage? Well, it's not normal for disks to really be transient. If they are, it's typically indicative of a bad disk. But that's not necessarily the case for cloud. Disks can come and go. They can get moved from one node to another. A node can move. The networks can change. And you really need to make sure that from a storage stack perspective, you can handle this very easily. The nodes themselves can change in all sorts of different ways, get moved. The regions can change. And so your storage system has to really be able to handle this. And how does it do that? Well, first you design it to handle all of that, but also you make sure that you're interacting directly with your CO. This is really your interface to the cluster that says, hey, this is the state of our system. This is what's changing. These are, this is where everything is. So if you need a current status of your cluster, that's where you're going. And so if you design your storage implementation, your storage stack, to interact directly with that, then you can gain all of these advantages fairly simply. So this really becomes a programmable storage system. As we were talking earlier, the applications are actually tied or wanting to be tied directly to their storage through these APIs. So in a lot of these cases, it's just a pod having a description of what the storage looks like, where the PV is, etc. And this is all gone through with the integration with the CO. You can also allow things like authentication, RBACs, and interactions with CI/CDs. An example of one of these is it's called the Open Storage SDK, which Luis works a lot on. Spends most of his days and nights doing. It's a gRPC storage stack. It's letting DevOps users integrate their storage interfaces with their application development. We actually have a demo. Do we have time for the demo? Okay, cool. Which is also going to use Katacoda. Can we still read? Cool. So I've just set up the environment already, which is just downloading some packages, preloading the VM with some of the libraries. What we're doing here is, in order to consume Open Storage SDK, we actually fire up a mock server. So you can set up your application to interact with all of these. You can set up your plugins however you want to interact with a mock backend before you develop yours. So it's really just as simple as clicking, maybe. Oh, and the demo gods are on me now. It's not clicking. Oh, sorry. Okay, so this was the first screen I was talking about. We have a bunch of demos on the Portworx Katacoda page if you guys want to check it out, but hopefully this will take only 30 seconds. So this is actually an interface directly into the VM that's running, so we can modify all of these pieces as we're running. Okay, cool. So again, it's just clicking, it's going to copy paste all these things. It's more of a tutorial than a demo, but if we skip all of the other pieces. So this has fired up a container that's running the SDK, the mock server for it. We can check to see that the server's still up, or is actually up. And then, yeah, this one. Yeah. And then actually enter the Python environment, and now we can actually, I could launch a Swagger which will interact with it, but I think we've all seen those before. Now you can, this one. Now we can actually load up our application real quick. This is just setting up gRPC channels, setting up the cluster interfaces, and then we can actually double check that it loads everything. Cool. All right, so I think everybody gets the idea there. We can come back for questions if we want. Cool, so I'll hand it back for the actual integration that I was referencing. Luis will kind of go back into more detail here.
Thank you, Kyle. All right, so now we saw those demos. We saw how simple it was for a developer just to go to a website. I want to try the storage system out. They don't have to install anything. They just go to Katacoda, try it out, try out the demos. They can type right on there, and they can get a good experience. So the next thing we're going to discuss is a little more complicated, but now, again, provides that interaction between the storage system and the container orchestration system. And that is by extending it, okay? And there's a couple of ways that we're going to extend it. We're going to talk about CSI in a second. We're going to talk about extensions, and extensions specifically to the scheduler. And we're going to talk about operators. I'm sure a lot of you have heard of that. So the first thing is that we're going to discuss is CSI. So CSI is a community project started out by the CEOs themselves, actually, to be able to standardize the model that CEOs communicate with storage system drivers, okay? And that was done specifically, I'll give you one example. This is not the real, like one of the main reasons, but this is definitely a big example, is that at the moment, without CSI, driver developers would have to write a driver in the code of Kubernetes. That means that they are bound by the Kubernetes release process. And any time that there's a bug or there's a feature that they want to add, they have to wait for the next release. And then they have to go through the same process. And so it has to be tied down. With CSI, what they have done is that instead, the CEO communicates with the driver through a gRPC channel. Now that the driver can be installed out of band, and it's now the responsibility of the driver developer to be able to create it. Now, the CSI itself is a spec. Once somebody defines a spec, then now it needs to be implemented. And I'm part of this team that is called the Kubernetes CSI Team. In the community, we have people from Red Hat, VMware, Google, where we all work together to try to enhance Kubernetes to support this new specification, and to add every single container, what we call side containers and so on, that can interact with the CSI driver, and on the other side, interact back with Kubernetes. Because we don't want Kubernetes itself to be changed to CSI. What we do is we add extensions to it. And again, we have some links here. I have sent out my slides on Twitter, so you can, all these links are now available if you see them there. Now, I get a lot of questions. For example, I have a question just recently on the emailing list is, when should I start writing a CSI driver? You should start writing a CSI driver now, if you're a driver developer. You want to be tied to understanding how is it that it works. It takes time to think about it. It takes time to figure out how your storage system is going to interact with this driver. But you shouldn't deploy your CSI driver into production, okay? Until hopefully by Kubernetes, I would say 1.13. Hopefully, we're working really hard for it, but it'll be GA by then. And then after that, you can put it in production. But until then, it's still beta as of 1.10. Okay, and I think it's still beta in 1.11 too. So we also have a page. I think I have it here. No, there's a docs page. And that documentation page has a bunch of drivers on it, so you can see a bunch of examples that are available to you. And you can see there's many companies that have CSI drivers already. So if you want to understand how one works, you can look at any of these and you can start from there. So, okay, so we understand now that we can extend the communication integration of Kubernetes with our storage system. That's cool. That's one way. It just means that as an application developer, when I want a volume, I ask the CO asks the storage system, it creates one, and everybody's happy. Okay? And again, that's like the, okay, that's fine. We need to go further than that, though. We need to start integrating intelligence of the storage system back into the CO. And that is done through operators. Operators is really a concept of having a smart application, smart container, that communicates in between to the CO for events, and then it does some work. Okay? Now, I have here, this is a resource from the YouTube talk from Aaron. So if you want to see the whole thing, it's available there. And again, that little for loop there is from his slide, so I give him credit for that. But it's really the key thing. It's the entire operator pattern is just from the same pattern as the controllers in Kubernetes, which means is like there's a desired state, there's a current state, and what is it that needs to be done to change it. Okay. So the way this works is that an operator, for example, could be that wants to install maybe a storage system, or wants to change the time, or wants to create volumes, or wants to make sure there's always 5 volumes available. You can do whatever you want, as long as you create it and then interface back to the CO for asking it through the APIs, communicating with it. Now you can also extend the operator to have interaction, not just with the user, but with other things. You could create your own objects now. They used to be called third-party resources. Now they changed the name to custom resource definitions, so we call them CRDs. But what this means is that if you're creating an operator and you say, well, I wish I could store state, okay? But I don't want to store state in my own database. I want to be able to interact and tell Kubernetes and say, I have my own object type, okay? And that my own object type, I want to insert it into Kubernetes. I want it to know what this type is. And then I want to give events on it. So for example, if a user or some other API creates a new API, a new object of that same type, like, again, like I want a new volume of erasure coding, or I don't know, whatever you want, the operator will get an event immediately on this object saying there's a new one of these, right? And then we'll go through the for loop saying, is the state of this satisfied? Is it not? Then you will go through it. The really nice thing about this, again, is that it is up to the developer to think about many ways to be able to do this. And here's an example of an etcd CRD, was as a user, or maybe I'm another operator that I need etcd. And instead of thinking about how I'm going to deploy etcd, I just deploy the etcd operator, and then through a CRD, I say, hey, I just want a size 3 etcd cluster with version 3.2.13, and it takes care of it for me, right? It got an event that the CRD was created, and it went ahead and executed it. Okay. So let's take a look at a couple of examples. We have quite a few examples on these. The first one is one we called Project Talisman. And this one is very portware specific, but the idea is one that can be shared by any storage system. And that is the idea of upgrades. Sometimes you want to upgrade your storage system, but you don't want to so much as ask the user to intervene. When for example, we could have documentation if you're a storage system that says if you're going to do an upgrade, these are the steps you need to do. You need to shut down all your applications, or move your applications from this node to that node, and so on. The users don't want to do any of that. They just want a simple button. And so what this is intelligence in this program to be able to communicate with Kubernetes and install things in Kubernetes that make the upgrade simple. One shot, one command, okay? And I'm not going to go through exactly how Talisman works. So that's not really the important part here. But the important part to notice is that it is creating and using services of the CO to be able to satisfy the upgrade. Okay? Let's take a look at another example. This one here, Project Quartermaster, is I presented it last year at Linux Vault. And the project has stopped working because I did that when I was at CoreOS. But this one was an operator that installed software-defined storage systems into Kubernetes. And what this one has is two operators, actually. It's based on two. And as a user, what you would do is you would define your cluster. I want a Swift cluster or Kubernetes, a GlusterFS cluster of 3 nodes, and I want Gluster to be installed on these 3 nodes with these disks. Go, right? And what it would do is say, oh, I want to satisfy this request. I see that it's not satisfied, going through the loop. It then would create the storage nodes that would send events to the other operator saying, oh, I see a storage node. I need to make sure that's satisfied. It will install the container, and then it will set up the entire cluster, okay, to be able to satisfy that entire request. So that was Project Quartermaster. And all this code, this is available through here, and there's an architecture document available there also. Let's talk about another one that we use in Portworx a lot, and it's called Stork. And this one here is really nice because this one can be extended for any storage system. And what this one is the concept that if you have 1,000 nodes, right, and you want to deploy your application onto this cluster with 1,000 nodes, you would like the Kubernetes to try to install that application as close as possible to the storage that is consuming, that volume that it has, right? Because if not, it may be too far. It may have higher latency. So what this is, the Stork project, is extending the Kubernetes scheduler. When Kubernetes says, I have all these nodes, I can put this container in. Which one of these should I use? Because Kubernetes itself doesn't have that concept, right? So Stork, what it does is it extends it and says, oh, just so you know, you only use N1, 2, or 3. Anything else doesn't have the volume. Okay? So then Kubernetes takes and looks to make sure that then those nodes are okay and deploys that application. Now that application now has an extremely fast access to its volume because it's on those nodes. So now let's take a look at cloud integration. So I'm not going to go through too much of this, but this again is the expectation of users on integration of the cloud, of the storage system with the cloud itself, using the APIs of the cloud to be able to satisfy requirements. One of the things is, what we do a lot is that the customer has a set of disks. They don't want to actually create the disk, the EBS disk. They just say, hey, just have your storage system, just create 10, 15 disks, I don't care, right? I just need the thing done. And so they want the storage system to go talk to the cloud to create the disk that is going to consume, right? Second thing is that when you have backups and restores, what they want is that they want the volume to be created that they use, and they want it to, at some point, have a snapshot, and that snapshot automatically taken out of the cluster and moved out into, for example, an S3 endpoint, right? So if anything happens to the cluster, they can restore back, and then can start again. But they want this automatically in the storage system. And lastly, one of the most important ones, and again, this takes me back when I started at CoreOS, and we knew that whoever has the technology to be able to move a container and its data together from one cloud to the other will be a winner. Because here's an example. The customers themselves have a blue-green deployment, right? They set up their one cluster with a new app, with the new data sets, and they want to move that whole thing atomically from one system to another. Either maybe they have an on-prem cloud and they want to move it to the external one where it's all public, or they want to move that back. But that idea of migration of an entire application stack, all the way from the application, all the way to the storage that it consumes, needs to be done easily. Now, this one here is really interesting, I think, for me. One of the things that we do today is that when we deploy any type of storage system, in the cloud, we ask users to immediately start paying the maximum amount for that volume, for that system. So if we ask, if the customer says, okay, I want a 10 terabyte, sorry, let's just keep it small, 1 terabyte storage system, then maybe we ask it, okay, then you start to buy, let's say 100 disks or so. And you start paying for that immediately to the cloud vendor, even though the utilization of that system is 0, right? Now, as time passes, we have a utilization change. Sometimes we go high and sometimes we go low. But the problem is that the constant of payment is the same, right? So what we want instead, or what the customer wants, is say, look, I don't want this. I don't want a constant payment to the cloud vendor. Instead, I want the storage system to understand its utilization. It knows what's happening, and it already has connection to the cloud. So can't it react automatically and be able to not consume as much storage when the utilization is so low, right? So we have this project, and this is a technology project, right? This is not a product. This is what we're doing as a technology project, and it's called Project Rico. If you want to know why it's called that, I can talk about you after. But this project, what the idea is that it changes the way we think about a storage system. Normally, when we think about a storage system, we're storage developers. We always kind of think about it in a way that we deploy it on-prem, meaning the disk is there and it's of a set size and that's it, right? But we don't think of it as like, no, when you deploy in the cloud, you have an API. You're able to consume on demand. And actually, I know of some vendors that are starting to add APIs to their appliances so you can consume less and more, right? So the whole goal of this project is to say, okay, as the administrator, I'm gonna set a min value of the storage and a max value, okay? So Rico, this project is going to allocate enough storage to reach that minimum value, that steady state. And then it's going to keep running and check the utilization. And it's going to have a set of watermarks. So it's going to say, oh, you're at 25%, that was my watermark. I'm going to remove storage. Oh, you're at 80%, that's a high watermark. I'm going to add storage to the system, okay? So let's take a look at a demo. And again, technology demo, not a product, okay? So let's see, you have it here already. So as you can see from the bottom here, we have the 3 nodes in AWS. And each of these nodes already has the minimum set, okay? And then on the top, what we're going to do is I just run my unit test program, which is going to run through this whole test. Okay, and what it's going to do first is it's going to pretend to send events raising the utilization value. Okay, and by raising the utilization value, the system reacts and says, "Oh, I need to add another drive," and it picks a drive. The algorithm is awesome. It has for loop. It picks a drive right now from the system, and it adds a drive to it. Right. It picks an instance and it adds a drive to it. And when it does that, then it communicates to the storage system and says, hey, I just added a drive. You should add it back to your pool. And as the system keeps getting you saying, no change, no change, no change, no events happen, and then more events continue happening, okay? And again, it keeps adding drives until it reaches its maximum set value, because the customer doesn't want to pay any more than that. It says, that's it, you can't add any more value, any more drives. And then what happens is that's nice, okay? The ramping up is easy. The coming down, that's the hard part. Now we are saying that utilization value has come down. Maybe it's after Christmas, right? Nobody's buying anything anymore. You don't need as many storage systems or instances. The whole thing starts coming down. Utilization starts decreasing. And then it starts, I'm not playing, that's why. I was like, oh, what the heck's going on? So it keeps going, and you can see now that it goes to the system and says, Rico says, hey, I'm decreasing the storage amount on the system. I communicate with the storage system and say, this disk, I want it out. The storage system can say no, because maybe it needs it, but the storage system can say, yes, that's okay. I remove it from my pool, get it removed. That's an okay coming back to Rico. Rico takes it and deletes it from AWS. And now the customer doesn't have to pay for that disk that was not used, right? It was not being consumed. So we go to the end. We go back when the utilization goes down to 0, and we go back to the 3 drives for the minimum state. Okay? All right. So this is our interpretation of cloud native storage. Now, we say that because there's been probably over a year now discussion on CNCF of what it means to have cloud native storage, right? But I think this is a good definition. It needs to be simple, right? It needs to be simple. Second, it must have a programmable interface. It must be able to be easily consumed by the application vendors. It needs to have an integration in the CO. It needs to know that it's living there. It needs to understand and extend the technologies that are in the CO. And then lastly, it needs to understand that it's living in the cloud. It needs to be able to use those APIs to provide new services to the customers. And when we create these two systems, when we create a storage system that understands the cloud, the CO, it's just awesome, right? So thank you very much. Any questions? Oh, we also have some stickers. So see us in the back if you want some stickers. But any questions on the other? Questions? Come on. One question. All right, go. So that's a GloSurface question, and I would, you should ask the GloSurface guys. But Project Rico is not a storage system specific thing. It just says I want to add like an EBS volume to your cluster and return it back. So I would ask that question to the GloSurface developers. Yeah. Any other question? We're good? All right. Thank you.